Hello students, in this video we'll discuss the forward Kolmogorov equation for a discrete Markov chain. So given a discrete Markov chain, x0, x1, xn, all the way down forever. And let's assume it's time homogeneous too, time homogeneous, to make my life a little bit easier. Okay. Over a discrete state space, over the state space 1, 2, all the way up to n. Okay. The question we're going to address is what's the distribution of xn? So question, what is the distribution of xn? Well, of course, given that x0 is something, right? So what we're going to do is this. We're going to define a vector of alpha n. And what is this vector alpha n? It's going to be alpha n1 all the way up to alpha n. And it's simply just what? It's simply just the probability. The first entry is just the probability that xn is equal to 1, all the way down to the probability that xn is equal to n capital. Okay, so it's just the vector that contains the row vector, which contains all the probabilities that correspond to xn. All right, now what we can do is I can construct a recursion for this. And so how do I construct this recursion? Well, here's the idea. If I look at alpha n plus 1, what is alpha n plus 1 at I? This is simply just the probability. I'll say j, actually, make it a j. It's the probability that xn plus 1 is equal to j. Okay? And so now what? So now this, by the law of total probability, is just a sum over all k going from 1 to n, of the probability that xn plus 1 is equal to j, given that xn was equal to k, times the probability that xn was equal to k. Okay? All right, so what is this over here? This, of course, is just my pij, or p from k to j. This is just the sum over k. P, I go from k up to j. And this, of course, is what? That's the k entry. That's the k entry over here of what? That's the kth entry of alpha n of k. So what this is now is this exactly is just the row vector alpha n. That's the row vector alpha n hit with the matrix over here, P. And so this is the forward Kolmogorov equation. So our forward Kolmogorov equation is the following. It asserts that alpha n plus 1 is just going to be alpha n and then P over here. So if I iterate this, so iterating this relationship, so if we iterate this to see that alpha n is just going to be alpha 0, the distribution at 0, then p n times. And so now the question becomes that I want to find the distribution of xn, I have to figure out how to compute the nth power of this matrix p to the power n, right? In the best sort of case, and we'll discuss this in future videos, the best case scenario, the best case is when p is diagonalizable, when p is equal to s times a diagonal matrix lambda times S inverse, right? In this matrix over here, if that's for diagonalization, it's diagonal. And then therefore, p to the power n for this situation is just going to be S lambda to the power n and then S inverse. And then under certain conditions on the matrix P, if, for example, all the entries in the matrix P are non-negative, if they're all strictly positive, then I know that this matrix over here is going to have an eigenvalue of 1, and all other eigenvalues are going to be less than 1. It's called an ergodic matrix. And for those ergodic matrices, finding the steady state equilibrium, or the question is what's happened as n goes to infinity, and trying to find equilibrium states for this Markov chain, it's a very important, oftentimes it's the case that when your matrix is ergodic, you can actually compute that limit and compute the steady states, and the steady states are unique in that case. And we'll talk about that in future videos. Thank you very much.